separate x squared minus 1 to antiderivative of x squared.
Yeah, let's do it. Yeah, what is it? From 4.9, what is it? Antiderivative of x squared minus 1, what is it? 1/3 x cubed, right? X cubed on 3, right? X cubed on 3. For this one, it's just x. Oh, maybe it's not wrong. It should be fine. We'll see. We'll see. Minus x. Now, that is an antiderivative. I could put a plus c, right?
Wait, why is it 1/3?
Because whenever you raise the power 2, you have to divide by that number. Remember the antiderivative process? The powers? Raise the power by 1 and divide by the power. That's what I did. Raise the power up to 3 and divide by the power. I tend to write it like this, though. I tend to write it with a fraction up front. It's just me. So 1/3 x cubed minus x. Now really, it would be plus c. But because you're about to take that expression, right? You're going to put in 4, and you subtract the same thing with 2 put in. The c's are always going to cancel. So you never write the c in this process. You could, but it's just worthless. Okay? So when it says any antiderivative, you're going to pick the simplest one, where c is 0. Right? Could be anything. We're going to pick 0 just to make this look as simple as possible, because it works for any antiderivative. So we'll just forget the c now. Once it is a definite integral, it has limits of integration, we no longer use the c. It's only for antiderivatives with the indefinite integrals.
Net area?
This is getting net area. Now, granted, in this particular problem, there's no negative area to add in. It's all positive. So it is the actual area in this case.
So I'm using solve net area?
That is what it's doing. It's just our example has no negative area. It's always net area. Any definite integral is always net area. So we have this, and now you write this. 2, 4. Right like that. I think we'll do it for a while now. Okay? So what does that say? This says exactly what this says, except here we have to actually do something. So now we're going to take the 4 and plug it in, right? So we're taking now f of 4, and we're going to subtract f of 2. So we plug in the 4, so we get 1/3. 4 cubed minus 4 minus, right? F of 4 minus f of 2, right? Just like the formula says. Upper limit minus lower limit. F of 2, 1/3. 2 cubed minus 2. Everybody see what we just did? Has never seen a definite integral before? Take the upper limit of integration, plug it in. There's your antiderivative at upper limit. There's f of b, right? F of 4, cap f of 4. Minus. Plug in the lower limit of integration into this expression to your antiderivative. There it is. There's f of a, that's f of 2. Now just crush the numbers, and it should be 50 on 3. Right? Equals. Well, let's see. That's 64. So we have 64/3 minus 4 minus 8/3. I guess I can use the parentheses down there. Minus 2. So we have 64/3 minus 8/3. That puts us down to what? 56/3? So we have 56/3. Negative 4 plus 2 is what? Minus 2. Wow, 2 is the same as 6/3. So this reads 50/3. Same answer we got last time. So I did do it right last time. Worried there for a second. Okay. That's the power of the fundamental theorem. We avoided all that limit taking, all the using the sigma notation and those properties and formulae for the sigma notation. And this also allows us to open up the spectrum to who knows how many different functions now. Before, with our sigma rules, we can only handle what? Polynomials, basically. Now if you want to take the area under sine or cos or any other trig function, or underneath an exponential or any logarithmic function, any of them, it's always this, antiderivatives. Okay? So that's part one of the fundamental theorem. Let's do another problem real quick, because man, that was ridiculously simple compared to what we did last time. We did that all night. So area under the curve was 50. Number 26. the integral they give us is 1 minus sine x as the integrand. So we have 0 to pi of 1 minus sine x dx. It says to sketch the graph of the integrand, shade the region of the net area that you are finding, then take the integral. Okay? So we do the graph 1 minus sine x. What is 1 minus sine? What does that look like? 1 minus sine x.
Is it 1 plus cosine x?
No. Oh no, you're trying to do. Oh, don't do any integration yet. I just want to graph that expression. 1 minus sine. I'm going to graph 1 minus sine. Flip it, raise it by 1. Okay. The negative on the sine function reflects about the x-axis. You have a reflection about x, and then a plus 1 in the front. You're going to raise the whole thing up 1. So originally, sine would have looked like that for the most part. You get to reflect this, so now it will look like this. I've not labeled any of the scale yet. And now you're going to raise it up 1. This value here was already at 1, right, when you flipped it, so that's going to be at 2. So now, hold on a second, what are these locations though? There's pi on 2, there's pi, there's 3 pi on 2, and there's 2 pi. Okay? So forth that direction. So our picture should look something like. At 1 and at 2. So at 1 is now the center of your sine function, right? It was at 0, the center was at 0. Now you raised it up 1, so now it's at 1. And it's starting at what? A low point. So you are here. And now instead of going up, it's going to go down, right? So I'm over here. And at pi on 2, it's going to intersect the x-axis, which is going to graze off the x-axis. And then it's going to continue up to pi. At pi, it'll be the peak of 2. That's not curvy enough. Sorry. Right? There's our peak at 2. And then at what? 3 pi on 2. We back at a what? Back in the middle? Oh, no, wait, so, whoa, no, sorry. No, that's not good. Oh, wow, that's so sharp. Sharp in a bad way. There, that's better. And then back down there at 2 pi. There, that's better. And that's our picture from 0 to pi. We only need 0 to pi, though. So 0 to 2 pi, we have this expression. There. Right? Flipped and raised up 1. That's our graph. Now we're supposed to find the net area from 0 to pi, so we have to shade this in now. So there's our area. The area goes to 0 right at pi on 2, right? Okay. And you get some more significant area on this side. Agreed? There's our picture. That's what we're looking for. So I'll truncate this now. I don't need this there. The other thing you should realize is that when you're dealing with definite integrals, if you include 0 and pi here, it is absolutely irrelevant as regards the integral. It does not care at all. Okay? So if you left 0 and pi